the presentation is based on the joint work which happened when I was visiting Lihum last September. So all of us happened to think about some important open problem, and it was very difficult. Of course, we couldn't solve it just for 1 month, and instead we considered, as like a warm-up step, we considered something easier than this famous open problem, and this is the result we obtained. Okay, so let me introduce the problem first. So it's a graph problem. The instance is an outerplanar graph, okay, and there is a positive integer d. And the question is whether we can add a set of edges which doesn't exist in the original outerplanar graph, such that the resulting graph G prime with these newly added edges has diameter at most d, while G prime remains outerplanar graph. Okay, let me explain the problem a little bit more. So I hope you know what planar graph is. Outerplanar graph is when the graph G has an embedding such that all vertices can be placed on one face, on the boundary of one face. So especially this specific face which contains all the vertices on the boundary can be made as outer face. So typically we can draw the outerplanar graph like that, and the edges may be like this or like this. But there is no vertex something like this, because this cannot be, yeah, you don't have a vertex like this. In diameter, okay, diameter is like the maximum distance, the maximum over all distances between two vertices in the graph. So I'll define it again later. So okay, this problem is, okay, we can understand this problem as a part of this graph modification problem tradition. So you can make many such problems. So a typical form of this graph modification problem is as follows. Given a graph G, we ask whether it's possible to add edges so that the resulting graph satisfies certain property. So this certain property can be especially one of the two types. So we want to add edges so that the resulting graph has Hamiltonian cycle, or it becomes interval graph, or it becomes a proper interval graph, or you can make it to become chordal graph. And okay, for these cases, so if you don't have any constraint on the number of edges that you can add, then actually you can add all missing edges, make it into complete graph. Then complete graph satisfies any of these property, right? Complete graph has a Hamiltonian cycle, complete graph is chordal, complete graph is interval. Is it proper interval? Yes, it's proper interval. Yes, so on and so forth. So we need an extra condition, which is so we want to optimize the number of edges to add. So this can be, so if you consider parameterized algorithm, for example, you can consider this number of edges to add as a parameter, for example. So the objective goal will be the number of edges to add, while preserving the property of the target instance. Another type of problem is to optimize the value of the graph invariant that you want to fall into with added edges. So in this case, you can add as many edges as possible, but you want that the resulting graph has some invariant to be bounded by D or K, something like that. So the problem I consider is such a problem. So especially planar diameter improvement is such a problem. So what is planar diameter improvement? So you are given a planar graph and a positive integer D, I want to add missing edges so that the resulting graph has diameter m mod d. Okay. So you want to add links while preserving some topological property. And because you want to still keep this the resulting graph G prime to be planar, you cannot add arbitrarily many edges. So you cannot add just any edges. If you don't have this last condition that G prime should be planar, if you don't have it, then you can again add all missing edges and make it diameter m mod d, by diameter m mod 1. This is impossible because we have this topology constraint. So this is actually a quite famous open problem, which was already posted in some textbooks and in some papers. So here are some facts about this planar diameter improvement problem. So first, when the embedding is fixed meaning that I want to add edges so that the resulting plane graph preserves the initial embedding that we are given. Right? For example, if your planar graph is given like this with some vertices on the outer face, and I'm also given the embedding like this. Suppose you're given a graph like that, then I can add edges like this or this, but I cannot have edge like this. Yeah. Okay. So, but when the embedding is fixed, there is easy two approximation algorithm. So consider given fixed embedding, consider every face and make a completion by making a star of the face. For example, and given this fixed embedding, then take any vertex. So take a face, take any vertex on the face, and make a triangulation that looks like a star. Then any shortest path between two vertices here and two vertices here, so should go through some faces, right? So if you consider some, and if the optimal completion, for example, if it looked like suppose that the optimal completion looked like this, and the shortest passage between these two vertices used this edge. Then you can replace this edge by using two edges that you filled in for this approximate solution. So increase the path in this alternative completion by almost 2, by the factor of 2. So this is a easy to approximation algorithm. So this problem is quite a naive problem, but we don't know whether this is NP complete or not, even when the embedding is given.
You do preserve outerplanar property?
So here I was talking about planar diameter improvement, so we want to preserve that planarity. Yeah. So not outerplanar. No. For outerplanarity, actually, so what we did is that the problem is polynomial. So, but it is known that this problem is FPT when the embedding is not fixed, because the yes instances is closed under taking minor. So if you know about minor, you can check it easily. If you don't know about minor, it's difficult to explain. So, okay, so it's known to be FPT, but it's FPT in the sense that if you want to check whether the graph can be made into planar of diameter mod d, then d becomes the parameter, and there exists an algorithm which runs f of d times some polynomial in the size of the graph where f is some function. So the fact that it is FET means that there exists some function f such that there exists an algorithm that works in this time. But what is this function and what is this algorithm? We don't know. So it's only existential result using a big meta theorem. So the question is, the big open question is whether you can make a constructive algorithm that works in this form of running time. So even, okay, so whether there exists such an algorithm, this is open. And if there is a FPT algorithm that runs in this time, then in particular, this function is dominated by g or n to the g of t in particular. But so the fact that there exists a FPT algorithm means that it should be solved in n to the f of d time, but we don't know whether we don't know any explicit constructive such algorithm. So if you can find such an algorithm, yeah, it'll be good. I tried for some time, but I couldn't make. So instead of taking this problem directly, we will consider special case of the problem where the given instance is outerplanar and you want to make an outerplanar graph. So there are some basic facts about outerplanar graph. So a graph is outerplanar if and only if it doesn't have k4 or k23 as a minor. Okay, if you don't understand what it means, it's okay. So I'm going to skip this minor, the part which uses these minors. And also we can assume that the completed graph, the graph obtained after adding edges, is maximal. Maximal in the sense that it is two connected and all interfaces are triangulated. So why can we assume that? Suppose that I have obtained a G prime, which is a completion of the graph, which is outerplanar and diameter most d. And if this is not maximal and not triangulated, then I can just add one more edge while not violating the outerplanarity, right? And this never increase the diameter. So you can always assume that the graph is two connected and interfaces are triangulated, meaning that it's maximal. Can I use the? Yeah. So here are some notations. Delta of S is when you're given a graph G. So I have so given a graph G. So for a set of vertices S, delta of S is a subset of vertices in S which has at least one neighbor outside of S. So it's like a gate of S which keeps the contact of S with the exterior world. Graph G, this is G. When you have S, then delta of S is the collection of vertices which are exactly the endpoints of which has some neighbors outside of S. Eccentricity of a vertex. So eccentricity of a vertex in a graph G is a maximum between the vertex U that we have specified here and for every other vertex. So you compute for the eccentricity of a specific vertex. You have specific vertex U. Eccentricity is that I look at all the distance between U and V for every V and take maximum. Okay. diameter is the maximum of the eccentricity. So in particular, so it's like I take the maximum of the maximum distance for every vertices. So in a different way, you can say that this is the distance between the farthest vertices in one graph. Okay. So in order to, I want to present this polynomial algorithm for diameter completion. So the way I like to present it is to see it as an extension of diameter computation of a maximal outerplanar graph. So, okay. So given a diameter of a maximal, so maximal G. So maximal is two connected and triangulated. So when a graph is maximal, it has many nice properties. Especially it has fixed embedding, and because it's outerplanar, it has 3 ways and most 2. Okay, it has fixed embedding and it has a specific structure which looks like a tree. So you can decompose the graph into a tree-like structure, and using this structure, you can compute the diameter in a bottom-up way. So I want to show it first, and then we can see how this algorithm, this is rather quite a naive algorithm, how you can extend this algorithm by introducing some new notation to solve a planar, outerplanar diameter improvement problem when the given graph is two connected. And then so from here I will show the algorithm for outerplanar diameter improvement when the given graph G is two connected. And then we will see what's the obstacle to make this algorithm work when G is one connected. So obstacles. And there is a technical lemma saying that these obstacles can be removed using some reduction rule. Obstacle can be removed. So this is the like a flow of our flow of our work. So at this point you can solve there. We now have a polynomial algorithm that works for one connected graph. But it doesn't work for disconnected graph. But for this, there are some other reduction rules that you can handle. But this is a bit more technical. So anyway, let's see. So let's see this first. So I have maximal outerplanar graph. I want to compute the diameter. I want to check whether diameter is MOST. It's the same. First, a naive way is to try all pairs and compute the distance. You can always compute the distance between two vertices in a graph. So why not for why don't we try for all pairs? So you have to try to n to the square pairs, right? Times the algorithm to run a shortest path problem. But outerplanar graph has extra nice property. So using this, you can have a better algorithm which runs O of n overall. So how does it work? So basically, okay. So the the nice property we are going to use to look at this dynamic programming algorithm is the following. So suppose I have outerplanar graph, and because it's two connected, it has a fixed embedding. This is like a basic fact. If G is outerplanar, which is two connected, then two connected outerplanar, then it has a fixed embedding, unique embedding. And you can easily find it. So we assume that I have the graph with this embedding, and I pick up a specific two vertices which are adjacent and whose edge lies on the outer face of this embedding. Okay. So it means that we don't have such a component connected to it. So the graph looks like this. Something like this. And when it's maximal, you can uniquely, so given two edges, S and T, on the outer boundary, you can uniquely find the vertex W such that S, T, U, W forms a triangle. And this part, let's call it H of S, is outerplanar graph. This part is outerplanar graph. And the entire outerplanar graph can be obtained by gluing HS and H and T on this triangle. Okay. So this fact may need some proof, but you can see it, right? So once you obtain a small outerplanar graph, you can apply the same principle again now on this edge which was a part of the triangle, right? So for this edge, this lies in the outerplanar graph H of S. SW lies on the outer boundary of H of S. So you can uniquely identify another vertex, now W prime, such that they form triangle, and the entire outerplanar graph can be obtained by combining two outerplanar graph on this triangle. Okay. And when you decompose an outerplanar graph in this way, okay, so suppose that I have, okay, you can now even, so for this edge, I can decompose into this outerplanar graph and this outerplanar graph, and okay, let's do it this way. And for this outerplanar graph, I can again identify another vertex W, triangle, and outerplane. You can decompose the whole outerplanar graph into two parts. One is this part. The other part consists of this single edge, right? And which is combined on this triangle. And then for each of these edge, you can do the same thing. This gives you a kind of decomposition. This gives you a decomposition. I'm going to use this decomposition. Oh. Okay, this is the decomposition I just, so we have a decomposition, and so And this decomposition gives you a partial order on the following tuple: u, v, and x, where x. So you can think of tuple u, v, x, where delta of x is exactly u and v. Right? So for example, in this case, so in this graph, so s, t, v of g is one such tuple. Okay, oh, well, I'll just let's take this as a such tuple as a convention, and for every x which is a proper subset of v of g, I have such a tuple u, v, and x where whenever x, the boundary set of x, delta of x, I defined it before, is exactly u, v. And for each such tuple, I can give a partial order so that u, v, x is dominating, is larger in the order if u prime, v prime, x prime are larger than u prime, v prime, x prime. If x is bigger, then it properly contains x prime.
So when you read the two components in a triangle, you compute the diameter of the new component. Maybe you need what vertex make some diameter in the small component, right?
Yes. So we will keep two parts. Well, I think I will explain this part later.
Okay.
Yeah. Okay. Then how many such tuples can we have? For every uv, okay, if uv is not an edge, so this is a maximal outer planar graph. So if uv is not an edge, then you don't define such a set. You cannot define such a set x. So I'll define this tuple for every uv which is an edge. So you have uv such tuple as many as the number of possible as the number of edges in such a graph. So you have linear number of such tuples. And so in the top, so I'll pick a random edge S and T, and by convention I take the tuple which consists of where the last component is the all vertices in the graph, and for W, which is the unique vertex W, such that STW is a triangle and the blah blah property holds. We consider S, W, some X, S, let's say, T, W, X, T. So when you have S and T, there is unique W, such that SW is a cut. So SW is a cut between a vertex set here and vertex set here, and XS is the vertex set which is on one part of this cut SW, and TW is a cut that looks like this. Then this tuple STV of G is bigger than SWX of S, and so on and so forth. Right. So considering all the tuples, you can make this partial order where, and in the last, the minimal element of this diagram will be like u, v, and the last components consist of the two vertices which forms the edge. So for every v, you have such a tuple. So our objective is to compute ECC u, v, x, which I will define in the next slide. And this ECC u, v, s, so our objective is to compute this some value ECC s, d, v of g for this top tuple. And this value can be computed using the value of ECC for the lower value using dynamic programming. Okay, so in particular, in the minimal element, the value of ECC can be computed trivially. So recursively, if you have computed all the lower value, you can compute the next value, and compute the top value, the ECC value for the top tuple finally. That's the plan. So what is ECC? So it's for every vertex u and v. Okay. So it's a set of pairs obtained by taking the maximum elements of the set, blah blah blah. So it means that for every vertex w in this graph, in the vertex set of G, I take the distance between u and w and the v and w, and you can have many such. You can have such pairs, as many such pairs as the number of vertices in v of g. But among these pairs, I take only the maximal elements. So, for example, suppose this is a graph and I want to compute ECC u, v. Then for this value, the pair would be 2, 2. For this vertex, the pair would be 1, 2. For this vertex, the pair would be 2, 1. But here, 2, 2 dominates these two values, so I take only 2, 2. This will become the ECC of UV in this case. So in this case, UCC will be like that. Okay. So this is what is explained in the second. So because of this, because I take only the maximal elements, the ECC of a set can be only one of these following form. Either the distance of a vertex to u and v are the same, or the distance, or there is a vertex which is farther to v than to u, or the opposite. Or there are both types of vertices. There is one vertex which is closer to u, there is another vertex which is closer to v. And this is all possible pairs. So, well, these lemmas basically says that this UCC, this table of UCC can be computed using this decomposition structure. So when you have ECC value for this set, ECC value for this set, and the entire graph can be obtained by combining outer planar graph on X of S, where the outer planar graph takes S and W as on the outer boundary, And if the outerplanar graph takes so the outerplanar graph on x, xt takes tw on as the boundary, and if they are combined as a triangle on the triangle in this way, then you can update ECC of the upper tuple using the ECC of these two tuple. You can imagine how it will go. Yep. Okay. So in particular, if your goal is to check whether the diameter is at most d, then it can be that the two vertices which achieve the diameter may be inside this graph, which has S and T as the boundary. Okay. Okay. So you may have two vertices which achieve the diameter in this way, or you may have a vertex on one side or another vertex outside of the boundary, so it may look like this. So the two vertices that achieves the diameter may look like that. So keeping record of ECC of S, T, X, X is the set of vertices here, can help you to potentially find the diameter between X and Y. Distance between X and Y. But to check whether the diameter inside for the induced subgraph on this set, you need to check whether the diameter on this set is bounded by D. But you can again do it quite easily. So suppose that this is the graph that I'm looking, then, well, this is a part of a bigger graph, but what I draw here is the set X, and this is XU, and this is XB. Then if the diameter, the two vertices whose distance equals the diameter is inside this area, then the path may either go through W, or it may not go through W, which means that you should go through U and then go to V and then Y, right? And then the distance should be like D, W. So for every D, U, D, W, which is in ECC, ECC of U, W, X, U, and for every D, V, DW, this is from U, this is from V side. Then I can check the possibility. So first of all, if X doesn't achieve some particular tuple that can be found in ECC, then it doesn't contribute to the maximum distance between any two vertices. So it's enough to check for every tuple in the ECC whether they can potentially contribute, they can potentially achieve the diameter D with some other vertices here. Okay, so the distance between, so for vertex which achieves exactly this D, U, DW is in this ECC table, Then we know that the distance between x and w is exactly dw to the u. Okay, I use this notation just to distinguish, just to say that this value came from ECC for u, w, x, u. So the distance is dw here. Here the distance is dw to the v. So it should be that in order for dwu plus dwv. So if the sum is bigger than d, then it can potentially violate the diameter. But maybe the distance here may be shorter. dv. Here the distance is 1. Here the distance is dv. So dv plus 1 plus du. So this is the length of the path that goes through w. This is the length of the path that goes through u and v. So if both of them are bounded by d, then we know that for certain two vertices which realize this tuple, the distance between them will be bounded by d. So for every tuple in ECC, we can check these two. The ECC can have at most two tuples, two different tuples. So it takes just constant time. So, and if this is bigger than so if any of these, so if the maximum of these two are bigger than d, then we can say that, okay, we stop because the diameter is already bigger than d on this subgraph. Okay. Otherwise, we continue. So this is what we have. So we have defined tuples u and v, and x is the set of vertices whose boundary is exactly u and v, and there are at most a linear number of such tuples. Well, okay, let's say polynomially many such tuples, and you can define partial order. And for one tuple, you can compute the value of ECC for this tuple using the ECC for the smaller one. So, and for the minimal elements in this partial order, you can compute it. You can compute the ECC easily because the minimal looks like u, v, the two vertices, and this is either 0, 1 or 1, 0. So these are the two types of ECC. Okay. So from here, the extension to outerplanar completion of diameter most d, if the graph G is two connected, this is easy. So if the graph G is two connected, what we need to do is to fill in the edges so that it becomes triangulated, right? Because it's already two connected. So again, we do almost the same thing. We define the same partial order on the same kind of tuples, but the point is that because now the graph is not triangulated, it can be that UV lie on a big face with many vertices on the boundary, and then I may want to compute the ECC. So okay, let's call this W1, W2, W3. So okay, so these, let's say that this is a set of vertices. So I have identified a vertex at X, and I have the tuple u comma v comma x. But depending on where we want to add edges to fill in the to fill in this face. So for example, I can add edge in this way, or I can add edge in this way. Okay, I need to consider all the possibility. So what we can do is for every W1 on the face here, for W1, I can define u comma W1 comma XU so if I'm considering these two set, so this in this case this is XU, and then another tuple I want to consider is v comma W1 comma the rest of the set x minus XU. Okay. So we want to consider all these tuples for every possible vertices. But still this is okay, so for W2 I do the same. W3, so on and so forth. But still, because this is the graph, because we assume that the graph is two connected, if you identify just one pair of vertices, say U and W, I can define the set of vertices which appear on one side and the set of vertices which appear on the other side. So once you fix the tuple to U and V, actually the set X that should appear on this side is uniquely decided because of and this is because of the two connectivity. So again, the number of tuples that we want to consider to compute ECC, no, now it's some different value. So the number of tuples that we need to consider is polynomial, which may be bigger than linear, which is still polynomial. Okay. Well, the problem is that instead of ECC, so we could compute it ECC because we have fixed graph, but now we want to consider all possible fill-in, like completion of the graph. So for each completion, they can yield different ECC table. So instead of ECC, we compute what is called ECC star, which is like the best potential ECC. Yeah. Okay. The ECC star is like a collection of best potential ECC U comma V comma X over all possible outer completion of this subgraph. This looks a little bit okay. You can imagine. I'm not okay. You can imagine what you want to compute here, and the good thing is that ECC star is not very big. Actually, there are only 5 types of tables that you can, 5 types of tuples that you can have for ECC star. So again, we do a similar thing. We compute ECC star for each of the tuple, and once you know the ECC star of, so given a tuple, if you know the ECC star for the lower tuple, then you can compute the ECC star for this value, and you can recursively compute it. Okay, so now And you may wonder when exactly we add an edge here. So if finally you have computed ECC star, which tells you that the diameter is at most d, then you can backtrack the ECC star, which gives you this satisfactory ECC star. And if it comes from this branch, then it means that you add on edge UW1 and UVW1. Okay? And you can recursively find edges in the lower bottom. So eventually this will give you a triangulation for the entire graph. So now the problem is when the graph is one connected, so there is a cut vertex. So here I said that the fact, so although for this tuple UVX there may be several branches that may contribute to the ECC star of this tuple, once you fix the W1 or vertex W1, there should be a pair, then you can uniquely define XU. So what does it mean exactly? Okay. So when the graph is two connected, and if you fix a vertex W such that I will declare that the entire outerplanar graph should be obtained by combining something from here and something from here, which is combined on this triangle, then the set here, the set which contribute to this UW side is uniquely decided, and vice versa. But suppose that, for example, suppose the graph is, this is the extreme case. So this is not two connected, it's one connected. Now we don't know what should, so it means that, okay, means that I choose the vertex W here, and I consider one branch where UW should be an edge in the outer planar graph, and WV should be an edge in the outer planar graph. But among such outer planar graph, you can take many XU and many XV. For example, okay, you can have many, maybe this is connected. You can have many XV. For example, this component, the vertices of this component may be part of this set. That should be considered here. Or you can decide to put this component into part of this set here. Okay. So, in general, if you have C connected components here, if you have C connected components here, the way that you can choose the tuple XU that you decide to be contained in one part of the final outer planar graph, such that XU the boundary is contained in UV. This can be arbitrarily many. So for every component, you can decide to put it, include it in this set or not. But, and we have just shown that the number of tuples that you have to consider to compute this ECC star depends on the number of the running time to compute the ECC star for the top tuple depends on the running time, on the number of tuples that appear in this partial order, right? So it's crucial to bound the number of tuples, especially the number of possible sets whose boundary is exactly UW, because the number of pairs is just n squared. So if you can bound the number of XU whose boundary is exactly UW, then we are done. And for this, okay, so for this we have this rather technical lemma, which says the following. So G is an outerplanar graph with separating vertex V. B0 is the, okay. So in short, it says that, okay, it says that if there is a separating vertex V which contains many, which is part of many connected components like this. So if you have like 10, if you have 100 such components, then you can order. You can order the components according to some criteria which you can recursively compute, and then declare that these branches don't really help to decide whether this is a yes instance or not. So meaning that, so this ECC star V, B1 up to BT represent these connected components which is attached to V. And ECC star is okay. Is some criteria that you can recursively compute. And if you order them, so we can assume that this ECC star has computed in the previous steps. And if you order them in this way, then even if you remove all these branches except for the first 7, whether the instance is yes or no is preserved. So it's kind of reduction. So what does it mean? So if you can do it, it means that for every vertex, for every cut vertex, there is 8, at most 8, okay, 7 connected components that are attached to it. So you can, this XU, so when you have U and V, if you have almost 7 vertices that looks like this, and now I want to make all the toples which where this X of U has exactly UV as their boundary set. Then how many such X can there be? So it's as many as the number of partitions of these connected components alongside U and V. But this is, so this part is bounded by 8, this part is bounded by 8. So there can be like just 2 to the 16 possible partition of these connected components. This is big, but still it's affordable. So I have bounded the number of tuples that appear, which can that we have to consider. Okay. Yeah. So you can do some algorithm. It's something you can imagine. Okay. So finally, yes, we have. So I didn't describe here, but there is some more things you can do when the graph is disconnected. So finally, you can reduce to the case when the graph is connected, and the running time is quite bad. So obviously, we are interested whether you can improve the running time. Also, the first approach we tried for this problem is to produce all minor obstructions, because we already know that the yes instances are close on the taking minors. So we tried to produce all the minor lists, but we have partial minor lists, but not for all. So this can be also an interesting question. Also whether, so for outer planar diameter improvement, we know that it's polynomial. So what about the planar case? Is it NP complete or not? This is again open. And any explicit FPT algorithm for this planar diameter improvement, or even a constructive XP algorithm, can be also interesting.
That's for the PDI, planar.
Yeah, for planar diameter improvement. So for outer planar case, we practically settled the case. So the only interesting thing is to improve the running time, but I'm not sure whether this would be really interesting. Okay, thanks.
Okay. Thank you.